Впереди нас ждет доклад от доктора Онга. Доктор Онг из Малайзии. Сразу уточню, что запись на всякий случай его доклада мы подготовили, то есть это будет не прямое включение, но после данной записи у нас будет прямая связь онлайн с доктором Онгом для того, чтобы также можно было ему задать вопросы. Доктор Онг является директором компании Associates.
Good morning, everyone. Hope you're doing well. Thank you so much for your invitation. I'm very glad to be here. My name is Dr. Ong, an engineer. So today I'm going to talk about the importance of three-dimensional finite element analysis by showing you a few real-life applications. I will divide my presentation into 4 parts. In session 1, I will show you how we analyze a foundation system for a slender tower. This is unique simply because the foundation system is a combination of triangle-shaped coffer and few ball piles within the coffer. Number 2, I will show you how to simulate the effect of constructions of ball piles to the existing structures. In session 3, I will show you how to model separation in between different wall panels. Number 4, I will show you how to simulate stabilizing a failed slope using span piles. Now, we have to know when we need to go into three-dimensional finite element modeling. It seems to me that it is not too difficult to be understood by an engineer on when to go for two-dimensional or when to go for three-dimensional analysis, but I was proven wrong. Many engineers try to avoid three-dimensional modeling, whether it is intentionally or unintentionally. Inevitably, we need to go for three-dimensional finite element analysis for the following reasons. Number 1, when your element cannot be simplified into two-dimensional model. There is no way we can model piles in two-dimensional model simply because the soil that is flowing around the pile is three-dimensional in nature. Any attempt to model piles in two-dimensional, like reducing pile stiffness or using embedded pile roll, result in getting error in output. Number 2, when your loading cannot be simplified into two-dimensional model. Number 3, when you want to know what is the interactions between one structure to the another structure, and one of the structure can only be modeled in three-dimensional model. Number 4, when you are seeking for an accurate answer. I will demonstrate one example in detail in the following slides. Now, figure 1 illustrates a pile abutment. Figure 2 on your right illustrates the layout plan of the piles below the abutment. Now, a structural engineer will always tend to model the problem in one-dimensional analysis to get moment in the slab, like what will be shown in the next slide. So, a structural engineer will model the slab in one street. The structural engineer will simulate piles using pins, and the structural engineer will model the reinforced soil wall with an equivalent line load applied onto the slab. Span 1 is a cantilever slab. Now, by doing so, one will get a bending moment at pin number 2 of 463 kilonewton dot meter per meter, or simply times the load by lever arm, you will get the bending moment. Now, if you are a little bit lazy, you model the reinforced soil wall above the slab as equivalent pressure applied onto the slab. The rest, you are still conducting the three-dimensional analysis. And the maximum moment in the slab is given in the figure on the right. The maximum moment is 231 kilonewton dot meter per meter. Now, if you model the complete reinforced soil wall above the slab in three-dimensional model, the maximum moment is only 121 kilonewton dot meter per meter. Now, you can see how conservative it is if you model the problem using one-dimensional element. You model the reinforced soil wall as an equivalent pressure, and compared to a complete real three-dimensional model is carried out, the difference is just huge. Now we go into session 1. It is about an innovative deep foundation system for a slender tower. The objective of these analyses are: number 1, to study the interaction between the board piles and the coffer. I will show you in great detail in the next few slides. Number 2, to determine the pie cap and the diaphragm wall coffer. Number 3 is to study the impact of basement excavation to the adjacent monorail piers. So we can simulate the problem in one three-dimensional finite element model. We are analyzing the foundation and the basement excavation for a high-rise building called Royal Lexis. It is unique since the building is very slender. The width of the building is 35 meters, but the height is 308 meters. The ratio of height to its width is 9:1. So the structural engineers were juggling with the design so that the building will not deflect too much to resist the wind loads. Eventually, the structural engineer decided to design 2 triangle coffers from the top of the building extended down to the ground level and go further down 75 meters into the soil to give the rigidity it requires. The foundation system is a combination of coffer in triangle shape and big diameter board piles within the coffer. We need to know the load transfer mechanism between board piles and the diaphragm wall coffer, and how much the shear force is developed in between the pie cap and the diaphragm wall coffer. This is the three-dimensional model. The size of the model is 240 meters by 300 meters by 156 meters in depth. The development is located within Canny Hill Formation, or simply a mixture of sandstone, mudstone, and shale with different weathering grades. All parameters were correlated to standard penetration SPT number. The groundwater table is about 3 meters below ground. These are the structural elements in this model. The 2 basement excavation is supported by a soldier pile wall. Board piles were 100 meters long. There are 3 board piles each within the triangle diaphragm wall coffer. Interface was modeled along the diaphragm wall coffer, except at the section connecting the pie cap to the coffer, so that we can extract the shear force and design for it. Pile foundation along the monorail piers were modeled so that we can output the induced deflection and forces in the monorail piles. I quickly walk you through the construction stage. We generate initial ground stress in stage 1. We then excavate the ground to form the present ground level in stage 2. We simulated the construction of bore piles, pile cap, and walls in stage 3. We simulated basement excavation in stage 4. We then apply building loads onto the foundations. And we consolidate the ground for 10 years. This is a fully coupled effective stress analysis. And we get the settlement of about 41 mm at the north coffer and about 36 mm at the south coffer. This is a settlement at pile cap level. The settlements are within 24 to 40 mm. You can plot the settlement trough from the basement wall to the monorail piles. The monorail piles are expected to settle around 8 mm. You can output the total displacement of every pier, and therefore you can compute the distortion angle in between piers. There is no net groundwater drawdown after 10 years of consolidation. We expect the soldier pile wall to move 21 mm, and we expect the diaphragm wall coffer to move 4 mm. Now, you can output many information from the analysis, but I would like to highlight this graph to you. The graph on your left is a plot of axial load in the triangle diaphragm wall against depth. You can see there is a sudden jump of axial load from RL31 to RL26 after the building loads are imposed onto the diaphragm wall and the bore piles. This is the developed shear force at area where rigid connection was modeled at interface of the pile cap and the diaphragm wall. The shear force is important so that the shear link can be designed to take the shear force. You also can output the distribution of axial load in bore piles, provided you model the load transfer curve for the bore piles, so that after the ultimate shaft resistance is reached, the load is transferred to the greater depth. I suggest you to read my paper to input the load transfer curve into my GDSNX. And now we go into session 2. It is about the assessment of ground movement due to construction of bore piles. The objective of the analysis are: number 1, to estimate the ground settlement due to bore pile construction. Number 2 is to estimate the induced deflection and forces in the adjacent piles. Now, sometimes you are constructing bore piles within a basement, and the basement is located next to the existing structures like MRT piles or tunnels, and the ground is in loose state, like what you have SPT less than 10. Many times you will notice that a significant ground settlement has been recorded during the construction of the bore piles, even before the basement excavation work even started, like what you can see in the settlement reading here. A ground settlement of as much as 12 mm had been recorded before the basement excavation work started. The ground settlement is mainly due to water drawdown in the boreholes, in which it is inevitably when you remove the spoils from the boreholes, and at the same time you also remove the slurry. And the second reason is the convergence of the boreholes itself. This is the three-dimensional model we developed to assess the problem. We model a strip of bore piles in loose sand with SPTN equal to 5. This is the structural elements of the model. The two pile groups on the right is the existing MRT piles, in which we would like to know what is the effect of the constructions of the new ball piles to the existing MRT piles. To model the ground deformation due to the constructions of the ball pile, we simulated the constructions of the ball piles. In step 1, we generate initial ground stress and water pressure. In step 2, we model the existing structure so that we can record the reinduced deflections and forces. In step 3, we then simulate excavation in the boreholes. At the same time, we apply fixity to simulate placement of temporary steel casing, and at the same time, we simulated rapid drawdown in the same boreholes. In step 4, we simulated the excavation process in the next pile, but at the same time, we simulated completion of ball pile by changing the property of the solid element to concrete property in the first pile. And the process is repeated until the last ball pile is cast. The figure on the right illustrates the bentonite pressure applied onto the boreholes. And in the same graph also you can see that the lateral soil pressure is slightly larger than the bentonite pressure. By carrying out this analysis, you are able to estimate the ground movement due to constructions of the ball pile. Now, as you can notice here, the maximum settlement does not happen at the longest pile or the first constructed pile, but at the largest diameter piles. This result aligns with our observation at site that the governing factor of how much settlement you will get is highly dependent on the diameter of the ball pile. And therefore, you are able to assess what is the induced deflection and the forces in the adjacent piles for further assessments. Now, I'm going to demonstrate how to model separation in session 3. Most of the time, we model diaphragm wall as a continuous wall. There is nothing wrong with that, provided there is Wheeler beam to distribute the load in between diaphragm wall panels. Diaphragm wall is formed by discrete panels. There's no reinforcement to connect the two panels together. Now, this is a 5-basement excavation for an automated mechanical car park in downtown Kuala Lumpur. There is a permanent lift within the basement so that no temporary internal struts and veiler are allowed except only a reinforced concrete strut that dividing the opening is allowed. So for this reason, buttresses were used to facilitate the deep excavation. We model the joints in between the diaphragm wall panels using Jensen's law so that the diaphragm wall panels is able to give way if the shear resistance is exceeded. By using Jensen's law, redistributions of moment and shear force in the diaphragm wall is considered. This is the 3-dimensional model for this problem. All the soil parameters were correlated to SPDN value. I quickly walk you through the construction stage. In stage 1, we generate the initial ground stress and the water pressure. Stage 2, install sheet pile and the diaphragm wall. Stage 3, carry out the first excavation. Stage 4, construct B1 slab and staircase. Now, this step is very important. We model rigid connection at the interface in between the B1 slab and the top of the diaphragm wall, so that we are able to extract the tensile force in the slab for the structural engineer to design the reinforcement to take the tensile force. Stage 5, excavate further down and install strut at that level. And the remaining steps are just the sequential excavation until the final excavation level is reached. Stage 6, excavate one more level down to RL 29.96 and construct slab and RC beam at the level. Stage 7, continue with the next excavation down to 27.52 and construct concrete strut at RL 27.52. Stage 8, continue with the next excavation down to 26.3 meters and construct slab and RC beam at RL 26.3. Stage 9, excavate to 23.9 and construct the concrete strut at RL 23.9. Stage 10, excavate down to RL 22.68 and construct the slab and RC beam at RL 22.68. Stage 11, excavate down to RL 20.27 and construct concrete strut at RL 20.27 meters. Stage 12, excavate down to RL 19.04 and construct slab and RC beam at RL 19.04 meters. Stage 13, excavate to final excavation level down to 13.67 meters and construct base slab at RL 15.3 and we consolidate the ground for 10 years. This is the total displacement at the end of excavation. We expect the wall to move 37 mm. The diaphragm wall will move 9 mm without any failure. You can see that there is opening in between the diaphragm wall panels when the shear resistance is exceeded. You also can see that the bending moment is redistributed at construction joint. The moment is much lower as compared to the rigid connections. For example, in rigid connections, you can see 647 kN dot meter per meter of bending moment is developed. At joint, only 72 kN dot meter per meter of moment is generated. And you can output the tensile force in the slab for structural engineer to design for reinforcement. Now this comes to the last session of the topic of reinforcing embankments on soft clay using spun piles. Since I have some data from the inclinometer, I will present the comparison of the measurement and the prediction. Now, embankment failure is very common in soft clay. This case history is unique because the embankment was very low. It was only 1.8 meter high embankment. The embankment did not fail immediately after reaching the surcharge level, but it only happened after 3 years after reaching the surcharge level. Now, this is the deep settlement markers reading. As you can see, there are few readings that show immediate and drastic settlement, such as reading in red and in magenta color line in the graph. This indicates bearing capacity failure happened during the filling of the embankment. The soft clay is sheared and transcends into residual strength mode. Now, you can do some back analysis and compute the residual undrained shear strength using limit equilibrium method. So from there, we can design some reinforced methods. On paper, by putting basal reinforcement, it shows it works, but in reality, it does not work. The embankment failed for the second time after we put the basal reinforcement and raise up the field. Then we design piles to stabilize the embankment. We model the embankment and the piles in three-dimensional model in a form of a street. The width of the model is equal to the spacing of the span pile in longitudinal direction. The construction stage is as follows. Number 1, generate the initial ground stress. Stage 2, construct the embankment in layers. Stage 3, consolidate the ground for 3 years. Stage 4, install the span pile. Stage 5, consolidate the ground for 30 years. So in short, we are modeling the deflections of the span pile due to post-construction movements. We model the soft clay using modified chem clay model and the crust using more Coulomb model. The idea is to get the model undrained shear strength as close as possible to the measured undrained shear strength from the field plane shear test. We further reduce the friction angle of the clay from 24 degrees to 18 degrees to simulate the remodeled undrained shear strength. Then we are able to simulate the ground settlement rate. The upper bound curve represents the predicted settlement without PVD, and the lower bound curve represents the predicted settlement with PVD. Our observations tells us that the real behavior is close to the upper bound curve, or in other words, the PVD did not function very well. From this analysis, we predicted the maximum deflection to be 75 mm, and you can see the shading effects kicks in. Now we look at the instrumentation's result. We install inclinometers into the annular of the span piles and in the soil next to the span pile, next to the embankment, and further away from the embankment. Now this is the deflection in the span pile next to the embankment. The measured deflection is represented by lines with markers. The red color line is our prediction using Midas GTSNX, and the blue color dotted line is the extrapolated deflection since the measurement is still ongoing. The lateral deflection at different level were plotted against time. You can see that the rate of deflection is tapering off. By using some mathematical function, you can predict the ultimate deflection from the measurement. This is the deflection in the inclinometer installed in the soil. The magnitude is very similar to the inclinometer installed in the pile. This is the deflection of inclinometer installed in the piles but further away. The deflection is smaller as compared to the inclinometer installed just next to the embankment. Similar magnitude of deflection was observed in the inclinometer away from the embankment. Then come to the end of my presentation. I would like to conclude my presentations with the following remarks. We say that Midas GTSNX is a very powerful and accurate tool. It helps engineers to make decisions. And it has been demonstrated that the software is capable of simulating complex geometry in three-dimensional model, and it can capture the interrelationship between the stress, seepage, and the air, or in simple word is a fully coupled effective stress analysis. And the software is also capable of model separation in construction joints. And that comes to the end of my presentation, and I would like to thank you for your patience and your time. Thank you very much.
Уважаемые участники конференции, мы снова в студии. Сейчас со мной наш технический директор Константин Скоробогатько. Константин, добрый день.
Привет, Кирилл. Привет, друзья.
Константин нам поможет в коммуникации с доктором Онгом. Он будет мостиком для задания вопросов.
Hi, Mr. Ong. How are you?
Hi, I'm fine. Can you hear me?
Yeah, sounds perfect. Thank you. At
Okay.
first, I want to thank you, Dr. Ong, for your innovative and engaging presentation. Today we have more than 300 participants online, and some of them prepared questions. If you don't mind, I will ask you a few of them.
No problem.
Okay, first I will read the question in Russian and provide with you the translation, and then I will translate your answer for our attendees. So here is the first question in Russian. В чем заключается преимущество использования центрифугированных свай для стабилизации склонов по сравнению с традиционными методами усиления насыпей? Рассматривали ли вы другие варианты? So question in English. What are the advantages of using centrifuged piles for slope stabilization compared to traditional embankment reinforcement methods? Have you considered other alternatives?
All right. The last example given in my lecture is actually a repair work for a newly completed expressway. Due to time constraint, stabilizing the embankment by installing a few rows of precast piles along the edge of the embankment can save you from removing and reconstructing the whole embankment. We have tried a basal reinforcement method, but it doesn't work. I think it is because of the large deformation problems. So we need something more rigid. So therefore, we propose to use the precast pile to stabilize the embankment. And for your information, the deformation now has stopped. So the deflections stop at 50 mm, 60 mm, so it works perfectly well.
Okay, thank you for the full answer. Now I translate it into Russian for our attendees. Итак, друзья, ответ доктора Онга был довольно объемным. Я попробую его тезисно вам донести. Собственно, доктор Онг сказал о том, что его последний пример был посвящен ремонтным работам на недавно завершенной автомагистрали. И в связи с ограничениями по времени стабилизация насыпи путем установки нескольких рядов сборных свай вдоль края насыпи могла предотвратить необходимость реконструкции всей насыпи целиком. Поэтому они попытались использовать дополнительно базальные армирующие элементы, но это не сработало из-за проблемы больших деформаций. Если вкратце, то ответ доктора Онга был в этом. Так, у нас еще есть несколько вопросов. So the next question in Russian. Как выбор модели поведения грунта, например, вы упоминали модифицированную модель ChemClay для слабых глин, влияет на результаты прогноза осадок и устойчивости насыпи? Почему использовали именно эту модель? So, Dr. Ong, question in English. How does the choice of a soil behavior model, for example, modified ChemClay model for soft clay, impact the result of settlement prediction and embankment stability? Why was this particular model chosen?
Yeah, for practicality reason, we prefer to use a modified ChemClay to simulate the behavior of soft clay and very soft clay to soft clay. With virtually, we need to input only a few input parameters. Actually, it's 6 input parameters only in modified templates. And all the input parameters can be obtained from the simple one-dimensional consolidation test. For stiff clay, a soft soil model can give better predictions of deformation. Now, another thing is it is very important to calibrate your soil model with some field measurement. For example, you can back calculate the undrained shear strength from the field venture test, or you can back analyze the inclinometer data. By doing so, you can predict the settlement and lateral deformation of your embankment in a fairly accurate manner. Normally, we check the stability of the embankment using a limit equilibrium method by using software like SlopeW. Yeah.
Okay, Dr. Ong, thank you for your answer. It was very detailed. Итак, друзья, я попробую донести вам мысли доктора Онга по данному вопросу. Собственно, из практических соображений модель модифицированного ChemClay достаточно хороша для описания поведения очень слабых глин, мягких глин, и данная модель подразумевает минимальное количество входных параметров. Она требует всего 6 параметров для ее описания. Для твердых глин модель Soft Soil также может давать более точные прогнозы по деформациям. И важный момент о том, что калибровка вашей модели грунта с помощью полевых испытаний будет иметь решающее значение. Например, по результатам недренированной прочности на сдвиг из полевых испытаний среза или по результатам обратного анализа для данных инклинометров. И также можно довольно точно предсказать осадку и боковые деформации основания, сложного мягкими глинами с достаточно высокой точностью, и обычно они используют упрощенное программное обеспечение для анализа предельного равновесия и используют также данные модели. Собственно, ответ доктора Онга заключался в этом, и у нас еще есть буквально минута. Я думаю, мы успеем еще рассмотреть короткий вопрос. Okay, Dr. Ong, the last question for you for today. Question in Russian. Какие методы контроля качества применялись при моделировании контактов между свайным ростверком и стеной в грунте кессона, чтобы обеспечить точность расчетов усилий сдвига? So, question for you in English. What quality control methods were applied when modeling the contacts between the pile cap and the wall in the ground, I mean D-wall maybe, of the caisson to ensure the accuracy of shear force calculations?
All right. For this problem, the pile cap is connected to a triangular shaped diaphragm wall. And along the diaphragm wall, we simulate the interface element along the diaphragm wall so that the diaphragm wall can fail if the load is exceeded. But the contact in between the pile cap and the diaphragm wall was modeled as a rigid connection. So what we did is we deactivate the interface at the contact area in between the pile cap and the diaphragm wall, so that we know the shear force developed at the contact area. And then we can design the shear link to take the shear force.
Okay, thank you. Если зарезюмировать ответ доктора Онга, коллеги, то он заключался в том, что контакт между оголовком свай и заглубленной стенкой, он был смоделирован как жесткое соединение, жесткая связь, и также интерфейсы в зоне контакта, они были деактивированы и не участвовали в расчете. На этом, я думаю, мы можем поблагодарить доктора Онга. Мы узнали довольно много об опыте применения в Малайзии. So, Dr. Ong, thank you very much for your answers. We have learned a lot about the principles and practices of geotechnical design. And thank you very much, Dr. Ong. I hope to see you at our future events. Have a nice day.
Спасибо большое доктору Онгу.
Yeah, thank you very much
Константину
for inviting me here. I feel
презентации.
very pleasure to be here.
Уважаемые
Thank you very
участники
much.
конференции, впереди нас ждет небольшой